Next, by using the differential equation of the voltage and current, we will discuss the energy stored in capacitors. For the reference directions of voltage and current as shown, we know the power absorbed by the capacitor is U times I. So it equals to U times C times du dt. Now let's consider the energy absorbed by the capacitor. From the negative infinity to the present time moment t is Wa equals to Pa integration. After eliminating the variable tau, this is the integral about u, and we can write it like this. Generally, we think the capacitor doesn't store energy at the moment of negative infinity, or no voltage, so this part is zero. Thus, it is equal to 1 over 2 times C times U squared U. If substituting U equals to Q over C, it can also be equal to this part. The value is always no less than 0. With this equation, we further specify that the energy change of the capacitor from moment T0 to T is equal to this. Similar to the serial parallel connection of resistors, now let's discuss the serial parallel connection of capacitors. In the circuit shown in this figure, we know that I1 is equal to C1 times du dt, and I2 is equal to C2 times du dt. Applying KCL on this node, we can get I equals to I1 plus I2 and equals to C1 times du dt and C2 times du dt, and equal to C1 plus C2 times du dt. So it is written as a form of I equals to watt times du dt, where the watt is Ceq. Through our previous discussion, we know that the concept of equivalent is that two equivalent circuits have the same form and parameters. So Ceq is equal to C1 plus C2. Now let's talk about the serial connection. For simplicity, we assume that the initial energy storage of the capacitor is 0. For the capacitor C1, U1 is equals to 1 over C1 times the integral of I, and C2 the similar. Applying KVL to the subcircuit, we have U is equal to U1 plus U2. So we got the expression of U. So it is written as a form of U is equal to watt times the integral of I. Where the watt is Ceq, that is thus Ceq is equal to C1 times C2 over C1 plus C2. With the preceding conclusion, let's talk about the circuit, where a DC voltage current feeds two capacitors with different capacitance values. We want to find U1 and U2. We can certainly write it as a form of US is equal to U1 plus U2 on the basis of KVL, we analyze it from the viewpoint of conservation of energy. That is, so we can get C1U1 is equal to C2U2. And further, U1 is equal to C2 over C1 plus C2 and times US. And U2 is similar. This is the first method. According to this, we can get a very important conclusion. Look at the equation. It shows that the charges stored are the same for the two series capacitors. How to explain it? Assuming the charges stored here are positive charges. Here are negative, here are positive, and here are negative. According to the properties of the capacitor, we know that the value of the positive charge is C1U1. The value of the negative charge is negative C1U1. This is C2U2 and this is negative C2U2. Since it is a node in the circuit, we can list the equations. That is, negative C1U1 plus C2U2 is equal to 0. It means that after the circuit enters steady state, the sum of the charge on the bottom plate of C1 and the top plate of C2 is 0. The left is the moment after steady state, and the right is the moment of negative infinity, when we suppose the capacitor has no charge, so it is 0. Solve the equation and use US is equal to U1 plus U2, we can also come to the same conclusion. Charge conservation is a common technique for solving circuits containing multiple capacitors. I hope everyone could be familiar with it.